The next example where we look at induction is related to flux. Now, if you remember, flux, this time we're going to talk electric flux. Before we talked electric flux, we're now going to talk magnetic flux. It's the same concept. It's still the measure of how much field passes through an area. So the flux equation, I'm going to put an M for magnetic flux. The flux is the integral of the field dotted with the area. You have to integrate if the magnetic field does not have the same value everywhere in the area that you're looking at. If you have a situation where the magnetic field is constant or has the same value, so we say it's uniform. If the magnetic field is uniform, meaning at any one instant in time it has the same value everywhere in your area, we can pull that out of the integral sign and we get simply B dotted with A. Now dot product, remember when you do the dot product you get a scalar answer. It's not a vector anymore. And also the dot product multiplies parallel components. Just as it was with the electric flux, the area vector is normal to the surface or perpendicular to the surface. So if this was my area, the area vector is perpendicular to that plane, so it points outwards. Now, Gauss's law, we can talk about Gauss's law for magnetism as well. Gauss's law was just the special case of flux, where we looked at the flux through a closed surface. But unlike electric flux, with Gauss's law by itself for magnetism isn't particularly helpful in solving for a magnetic field, for example. When we looked at Gauss's law with electricity, we were able to use it in some situations to solve for the electric field. It won't work for magnetism. Reason why? If we imagine, for example, we have a bar magnet, north and a south end, we know the magnetic field comes out of the north end, wraps around, goes into the south end, continues from south to north inside the magnet. If we draw some sort of imaginary surface, a closed surface, say, for example, a sphere. If I draw a sphere. Oops, I forgot to continue my field inside. When we draw our imaginary surface there, with the way I've drawn it, I have two lines coming out on this side, but those lines wrap around and come back and enter back in on this side. Whenever we have magnetism and we're looking at Gauss's law, we will always have the same number of lines leaving as entering. So the net flux is always 0. And that's why this equation isn't particularly helpful in finding magnetic field. It's always going to equal 0. And it's not that the magnetic field is 0, it's that when you sum up all the fields passing through the area, the net answer is 0. Flux, on the other hand, through just a two-dimensional surface, something like this, is actually quite important and applicable in our lives. For example, I have here, this is a galvanometer. It measures current and voltage. It's kind of old school, a little bit older than probably all of us. But that's okay, it still works great. So I'm going to hook it up so that it is measuring current. I'm going to hook it up to, this is a solenoid. This has copper wire. It's wrapped with electrical tape, so you can't really see the wire go around, but the wire wraps from one screw up here, it wraps around the solenoid 55 times, and then hooks to this screw over here. So between here and here, if we apply a voltage difference between those 2 points, so even if I hooked up a battery, it would make current flow through this solenoid. Okay? We have an area right here. So we're going to talk about flux through that area. Right now, if we ignore Earth's magnetic field, there's no flux through this area because there's no magnetic field passing through it. But I've brought some pretty strong magnets. These are neodymium magnets. They're actually, it turns out the better the magnet is, the more brittle the material, so these guys are kind of falling apart. That's okay, they still work. Now, I don't know which end is north and which end is south. Doesn't really matter. If I bring these in and close to that area, the field from here is going to pass through that area. You all right with that? So since there's a magnetic field passing through the area, there will be flux. Okay. Now I have no voltage source hooked up to this. There's no battery, there's no wall outlet.
Will the Earth's magnetic field always be more?
It's constant, so it's not, at any one location it will be constant. So I'm going to show you it's what's changing that makes a difference. The field, Earth's magnetic field is pretty small too, and that's why we don't see a noticeable effect here. Okay, so right now I've completed the loop. So now there's a complete connection between this screw and this screw. So there's a complete loop for charges to move through. There's no battery attached to it. It's not attached to the wall. So there's currently no current flowing through it because there's no potential difference. But if I bring this magnet in, so I bring it in, I don't know if you saw that little blip. If I bring it out, I get a little blip. Bringing it in, it blips one way. Taking it out, goes the other way. But notice, if I bring it in and hold it still, nothing happens. It's only while I'm in the process of moving this magnet that I get that little reading. Okay? It will work too if I move the actual coil and leave the magnet in place. We're getting current when we move either the magnet or the coil. That is an induced current, which means there had to have been an induced voltage, because current won't flow without a voltage drop. So what's happening is I'm inducing a voltage in here in the process of moving. But going back to motional EMF, these are, it's a conductor. The solenoid is made of wire, which is conducting wire. If it moves through a magnetic field, the force on the charges causes them to move. Okay? We can also state this in terms of a changing flux. As I move the coil or move the magnet, whichever one, the flux is changing. Because the magnetic field is strongest closest to this magnet, and it gets weaker and weaker and weaker the further away you get. As I bring the magnet in, I'm increasing the flux. As I take the magnet out, I'm decreasing the flux. So we actually get an induced voltage if we can change the flux through our coil. And we can change it either by moving the magnet or by moving the coil. Okay? I have another coil, same general setup, only this one has 880 turns. This one only had 55. So 880 turns on this guy. So bring this in. Our blip isn't so little anymore. The amount of current that flows is much larger the more turns you have. Which should make sense. The more turns you have, the more charges you have in there in general that can move around. So we get more current. Turns out, this works again, even if I just move the coil. And the reading will be bigger the faster I do it, which is kind of hard to do it fast. My aim's not so good. If I do it really slow, if I move my magnet really slow, my reading isn't as big. So if I move it really slow, I get a smaller reading than if I moved it fast. So the voltage that's being induced in here is entirely dependent on that flux changing. And I can make the flux change by either moving the magnet or by moving the coil. There just has to be some sort of motion. The equation that describes that induction is called Faraday's law. We're using epsilon again to represent an EMF, meaning a voltage, a potential difference. This is an induced voltage. It's not from a battery, it's not from a power source, but it does exist as long as we're changing the flux somehow. The equation looks like this. N being the number of turns we have. So we saw that when we used the 880 turns versus the 55, the result was a lot bigger. So the induced voltage does depend upon how many turns of wire you have in your cell. dphi dt, the derivative of the flux with respect to time. That is the rate at which the flux is changing. How fast you change the flux is important. Faster you change it, the bigger the induced voltage will be. So this is an induced voltage, or induced EMF.
So where's the speed?
It's within the derivative of anything with respect to time implies a speed of some sort. Not v as in speed in meters per second, but it's a rate. It's how fast things are happening. So it's within that derivative itself. In this case, since we have a complete circuit, since we've connected the two screws through the, in this case it's acting as an ammeter, if you have a complete coil, a complete loop, then you can induce current as well. And from Ohm's law, we know current is the EMF over the resistance of the coil. This would be our induced current. Now this negative sign is a law in and of itself. We call it Lenz's law. Now, just saying a negative sign isn't really, it's what that negative sign means is what Lenz's law is. If you remember here, if we move the magnet in one direction and then the other direction, we get a different current. With the needle going that way means current's flowing one way, with the needle going the other way means current's flowing the other way. So current flows one way, depending upon whether I'm bringing the magnet in or taking it out. But it also, if I turn my magnet over, it goes backwards than what it did before. Lenz's law tells us that the induced voltage, or if you want to talk about the induced current, is always in a direction to oppose the change in flux. So that negative sign is the opposition, to oppose change in flux. That means, for example, as I bring my magnet out, what's happening to the flux? Is it getting bigger or smaller? So magnet was already in, and I'm pulling it out.
It's smaller.
Flux is getting smaller, because I get farther away, the field's weaker. So the flux is getting smaller. What the Lenz's law means is that we're going to get an induced current that's going to try to increase the flux back up. It was perfectly happy with what it had. and it wants to get back to that state. So it induces a current to try to get the flux back to where it was. When I bring the magnet in, the flux is increasing because it starts out weak, or zero at this moment. As I bring the magnet in, the flux gets bigger and bigger and bigger. So the current flows to try to make it smaller again, try to oppose the change in flux. So that's what that negative sign means, is the opposition of the change.
In the end, that was the number of turns.
Yes. So for example, if we had a way to describe how this magnetic field is changing as I bring it in. It's getting bigger and bigger and bigger. Let's say let's just make something up. The magnetic field at the location of this coil versus time, it's going to start out small and it's going to get bigger and bigger and bigger as I bring the magnet in. So let's make up a function. I'm not in any way claiming that to be the real, actual magnetic field from my magnet. So let's just say the magnetic field is getting bigger with time. It starts with the value of 4, and it increases as time goes on. We have 880 turns. The area, this looks like it's about maybe 5 centimeters across. So the area of that coil would be 5 centimeters times 5 centimeters, it's squared. So 0.95 meters squared. So the cross-sectional area is 0.0025 meters squared. Let's find, if that were the magnetic field, let's find the induced voltage in this coil. Yes. It will not have an effect on the induced voltage, but it would have an effect on the resistance. So it would help determine the current. That's why I'm asking for voltage, is because I don't have, I mean, we can make up a resistance, certainly. So what is the induced voltage as this magnet is brought in? Well, induced voltage depends upon the number of turns. That's easy enough, we have that. But it depends upon the derivative of the flux with respect to time, the rate at which the flux is changing. So number one, we need to know the flux in order to take the derivative. The flux will be our magnetic field. It's changing with time, but we're assuming it's constant at any one instant in time, that it has the same value everywhere in that little square. Okay. The only time you have to integrate the flux is if the magnetic field has different values at different points at the same time. So here we're taking B times A So our flux is changing with time. It's getting bigger and bigger as time goes on. Which is why we get an induced voltage. If the flux was constant, we would not be able to get an induced voltage. Right now, there's flux. The magnet's sitting in there. There is flux in that coil, but the flux is not changing. which is why we're not seeing any reading on the meter. To find the induced voltage, we have the number of turns. We need to take the derivative of the flux with respect to time. Well, derivative of 0.01 is going to be 0. The derivative of this is going to be 0.015. So that is the derivative of our flux with respect to time. So the induced voltage will be negative number of turns times the derivative of the flux So the induced voltage would be 13.2 volts. Which, if we have the resistance of the coil, the R value, we could easily find out how much current was induced in that coil.
And the flux will only be free that goes through the center and has no effect on the outside of the coil.
Right, if I bring this way, I get a tiny bit of a blip, because the magnetic field isn't just straight down, it wraps out. So as long as I have any change in the field that goes through that coil, I'll still get a reading. So even if I move it out here, I get a little bit. It's not as big as if I move it in here. I can also get one if I just pass it over, which is kind of cool. I can actually feel a little tug on the magnet as I do that. Okay. This is actually applicable in many ways in our lives. It's how your credit cards work. The little strip on the back is magnetized. And when you swipe it through the little card reader, there's little coils in there to read the change in current. You get an induced voltage, an induced current. It's how the motion detectors work. And the security, like at the airport, those big, the security gate thing that you walk through. Thank you. Metal detectors, that's how they work. It's on a motional EMF. It senses the motion there of any metal going through.
So you should walk through it really slow if you don't want it to go off.
Yes. But I had a student that was a TSA. He worked at the security gate, and they'd get really bored, and so for fun they would see how slow they'd have to walk.
Yeah.
And he said, you had to walk like this. So I have a feeling you would raise some other flags.